Hi everyone, welcome to Power Electronics session number 19. In this session we are going to discuss about DC to DC converters. So DC to DC converters converts the fixed DC to variable DC, also called as DC transformers. As we know that in case of DC we can't use the conventional transformers. We can't get the output at the secondary of the transformer. But how to convert the voltage levels in DC system? We need to use DC to DC converters. Broadly, we will have like two types of DC to DC converters, but most of the times people will use the same name, like in both the cases. So that's why no need to stick with this classification, but we will actually discuss in our session in this way only. DC choppers and SMPS. SMPS is nothing but switched mode power supplies. Okay, that's it. So what exactly these are the things? So DC choppers means thyristor will be the main switch to control the output. Will be used to control the DC motors. That means these DC choppers will be used to control the speed of the DC motors. And here filter is not mandatory due to armature inductance. Generally, any power electronics converter will not give you the direct required waveform. So we will have unwanted components. In case of DC, we will call it as a ripple. In case of AC, we call it as a harmonics. Those will be generated due to switching action. So those has to be removed. To remove that, we require the filter. But in case of DC choppers, armature inductance is sufficient to filter out those. But in SMPS, MOSFET or IGBT will be the main switch to control the output. Okay, so sometimes we can use the BJT also, but mainly we will use MOSFET. So this is a very important one, because SMPS will run at very high switching frequency to have the less ripple and all that we are going to discuss in the subsequent sections. But MOSFET will be used. Will be used for IC chips, especially resistive loads. So in case of resistive load, if you use the output as it is, means it will have a lot of ripple in the output. To get the constant voltage for the resistive loads also, we need to use the filter. So filter is mandatory in case of SMPS. Okay, so first our discussion is mainly on choppers, then we will go on to the SMPS. So in case of DC choppers, we have like two type of converters. One is step down chopper, other one is step up chopper. Step down chopper is actually like it's just like a step down transformer in case of AC. That means average output voltage is less than or equal to input voltage. That means here you can see that it will be just like this. Output voltage will be less than or equal to input voltage. That means that is the step down transformer line. So will be used to control the speed of the DC motor, nothing but motoring action. Okay, when it is DC motor is operating as a motor, it will be like the speed will be controlled by this one. Step up chopper, in this case it is just like a kind of like a step up transformer. In this case, output voltage average value will be more than or equal to source voltage. So that's what. So this will be used to control the speed of the DC motor during braking. That is called as a regenerative braking. That means motor will be operating as a generator. So this is generating action. So these are the two things. This will be used for the normal motor application. This will be used for braking application. So moving on to, we will discuss mainly, we'll discuss about DC step down chopper with R load, then we will discuss with the respective loads. So if you take this chopper like this, we discussed already this kind of circuit diagram in commutation circuits, but we didn't discuss about the operation. Now here, if you connect this voltage to the load through these switching, so we can actually like get the variable output voltage by turning on and turning off this switch. That's why this chopper action, that means we can get the variable output voltage by operating with this switch. Okay, so that's what this switch will be turning on, turning off, turning on, turning off. Then only we can get that. So that's the meaning. So that's why it is called as a main switch. This is the main switch. We will actually turn on and turn off this one. Okay, so this diode is required to have the constant load current. That's not much. This is a freewheeling diode. You can call it as a freewheeling diode, like we discussed in case of rectifiers. So now when the switch is on, we'll see that what will be the equivalent circuit. Okay, when switch is on is nothing but during T on duration. In this case, this switch will be turned on and it will act as a short circuit, and this polarity will be like appear here. That means source voltage will appear across the diode, that is like a positive and negative. That means diode is connected like this, means it is a reverse biased and it acting as an open circuit. So now in this case, output voltage will be like same as a source voltage. That means output voltage V0 is same as VDC. Okay, that's one. So that means when switch is on, source is supplying energy to the load. So now to control the output voltage, we need to turn off this switch. When you turn off this switch, that means during half duration of the switch, that will be represented as a T off. In this case, switch is off and diode will also be off because the load is resistive. That means this diode will be in conduction whenever there is a storing element here. That's especially inductor, but there is no inductor here. That's why this is also open circuit, because load is here. Resistive load means it is a energy consumption, no energy stored here. That's why here output voltage during this period, instantaneous value, this is 0. So this is capital is nothing but average, instantaneous will be small letters. Okay, in this case, if you take this one waveform, you can see that like how the output voltage waveform will be there. Okay, this is actually the plot we are taking that. So this is the time t and this is V0 we are taking that, and this is for resistive load. So as I told you that during T on duration, you will get output voltage is same as source voltage. So this is actually nothing but on duration of the chopper T on. So next T off, there is no voltage, that's why it will be 0. Again, if you turn on the switch, you will get VDC, turn off the switch, you will get V0, like that. So this is nothing but off duration of the switch T off. Okay, so completely this one will be taken as a total time period of the output voltage T. Okay, so now here the load is resistive load, then current will also follow the load voltage exactly. If you take the load current, that's a red waveform, is like this, exactly similar to this one, but it is same as voltage waveform. Okay, so this will be the voltage and output voltage and current waveform. Okay, these will be, so that is one. You can see here, you can, like if you're operating turning on and turning off, you can see here we are not getting the constant voltage. How to get the constant voltage? That's where we need to have the filter. So but DC to DC choppers are not meant for the resistive load generally. Those are meant for speed control of the DC motors. We'll see that further how exactly we are going towards RL load. If you take RL and RLE load, as we discussed already in rectifiers, if suppose load current is continuous, then obviously there will not be any difference between RL and RLE load. So that's what we are talking about. Okay, but one difference we discussed, that's nothing but in case of RLE load, current waveform is exactly similar to RL load, but it will be having the lesser magnitude. Okay, so same thing we are discussing about. If it is on duration, then it will be in off, like it will be in short circuit mode, then source voltage will appear across the load. That is nothing but, as discussed in the previous circuit, here also output voltage will be source voltage. During this period, inductor, whatever the inductor is there in the load, that is in this case or in this case, will be getting energy from the source. Okay, that means when the switch is off, main switch S is off, then this inductor actually forcing this diode to be turned on. Now this in this way, so this source load current now flowing through the diode like this. So during this period, even though inductor is actually supplying energy back to the source, back to the load, but here load is short circuited by the diode. That's why output voltage will be 0. But current will be there. That current is nothing but, here in this case it is actually inductor is getting charged by the source. Here in this case inductor is getting discharged by the load resistance and back EMF. So if you take the waveforms for this also, you will get more or less same thing. That means this is output voltage V0 and this is the time t. So in this case, output voltage will be same, no difference. It is as same as the resistive load, but current waveform is different. That means during this way, inductance is getting charged and RL load or RLE load is connected to the DC. Exponential increment will be there and then exponential decrement, because during this period inductor is getting discharged and again charge and discharge like that. So this is the current waveform. If you're having more and more inductance, then it will be almost like a constant waveform. So this is what. So here also, so you will have the same thing. That is nothing but like this is during T on, and this is during T off. Main difference between the resistive load and inductive load is only current waveform. The voltage waveform is similar, and if you consider the RLE load, exactly you will get the same waveform, but current is also same, but current lesser magnitude will be there. That's it. That's why we consider this waveform is for both. Now, if you consider all the loads for the DC step down chopper, so this is like a kind of resistive load, this is for R load, this is for RL and RLE load, because it is same for both if it is a continuous current conduction. So that means this is like maybe you can take this is a continuous current conduction. And if you have a discontinuous current conduction, so this will be like this. This is discontinuous current conduction mode. So in this case, I am giving only for RL load. Okay. So here what will happen? Inductor will be getting charged, and then actually it will start from 0, because first time it will be, and it's the current comes to 0, then it will be okay. So like this. So now this inductor is getting charged, and then that whatever the inductance is there, that inductance is not sufficient to keep the diode for entire half duration. That's why this current comes to 0 and it stays in 0 for some time. Then again it will start from charging inductor during T on, when switch is actually on, source will supply the energy to the inductor, and again it will be like. So here the main difference between these two is nothing but more inductance here, okay, here less inductance. So inductance is less means current comes to 0 here. Okay, that's the meaning. So here, as we discussed already, this is nothing but like a T on, this is T off, okay, and this is total duration T, that means time period of the output voltage. Okay, but here some in the total T of duration, diode will not be in conduction. Okay, diode will be turn off in between. So that's what. So here the main difference between RL and RLE load is only during this period. Okay, during this period is nothing but, in this case current waveform is similar, but only the difference is output voltage waveform will be, the induced duration will be equal to back EMF. Okay, so but now I'm not considering the discontinuous current conduction. Forget about that, because if you want to calculate the V average for that RL load discontinuous current conduction, we need to know what is the duration here. So that's why. So with all these loads, I'm confirming that output voltage waveform is similar. That's why we can calculate the average value of the output voltage. Average value of the output voltage is nothing but area under the curve divided by total time period. That's nothing but VDC into T on divided by capital T. T on divided by T generally represented as a D. So D into DT. So VDC. So this is the average output voltage. Okay. So that means here D is nothing but it's a duty cycle or duty ratio. It is nothing but T on divided by. So that means you can say like D, you can take it as a T on divided by T on plus T off. So that you can take it as a on duration divided by total duration. So like that. So that's what. So once you got the V average, you can calculate the I average. I average is nothing but V average divided by resistance. This is for R load only. Okay, sorry, R load and RL load. In case of RLE load, as I told you that it will be similar output voltage etc., but current will be little different. That is nothing but V average minus back EMF divided by resistance. So this is for RLE load. Okay, so that's what the difference is, only this one. So another important thing we need to remember here, how to control this output voltage. So average value of the output voltage is D into VDC. This is constant, you can't change. Only you can change either by changing the numerator of the DT ratio. By keeping this constant, you can change the output voltage. That means D can be changed. So that is generally called pulse width modulation. Or you can also do that keeping the numerator constant, you can change the arc duration. If you are changing arc duration, is nothing but T is changing. T is changing means frequency will be changing. That is frequency modulation. But most of the times we will play with only pulse width modulation. That means width of the output voltage. There is a T on. So pulse width. So most of the times we will keep the total time constant because that is actually related to frequency. If frequency is changing, then filter coefficients will be changed. That's why we will keep this time period constant, and we will actually change the output voltage by changing the T on. So that's what we can do. Okay. Now moving on. Assume load current is almost constant, having inductance in the load. Then you will get like this. So as we already discussed, this is nothing but T on, this is T off. Okay, so we can actually take now in step down chopper, if the load current is constant, then what will be the waveform for diode and thyristor current, or maybe source current. Okay, so if you take that, this is nothing but this is the current waveform for thyristor. Okay, you can take that like a kind of like maybe you can take this one as a IT or IDC. That means source also same, because you can see that when the thyristor is in conduction, load current, source current, thyristor current all are same. That's what here. So that means here you can see that whenever the thyristor is in conduction, whatever the current is drawn by the load is coming from the source. That's why source current or thyristor current will be same. Next one is diode current. Diode will be in conduction when the thyristor is in off state. During that time, whatever the load current is there, that is maintained by the diode. So this is nothing but diode waveform for the constant load current. So if you take the average value of these things, means thyristor current average value, that is nothing but IDC also, because both are same. That's nothing but area under the curve divided by time period. Area I naught divided into T on divided by total time period. This is total time period. So then again you will get that D times I naught. So you can see that diode average current is, you can, because these are the average values. Average values is nothing but total I naught minus average value of the diode, source current will be the diode current. You can take like that, or otherwise you can also take like it is nothing but I naught into area under the curve. Area under the curve is I naught into T off divided by total time period. So that can be taken as a ID average values. T off divided by T is generally represented with 1 minus T. Okay, so into I naught 1 minus T. Why? T off can be taken as a T minus T on. So T gets cancelled 1, and T on divided by T is nothing but T. That is what we can remember. So this one and this one you need to remember. Okay, so there is another thing in this case. If you take it that one also, then like a kind of like if it is a continuous current conduction, and assume that thyristor is not like ideal device. Ideal device is not there, means what will happen during that time? That means when the thyristor is in conduction, you will get that VDC minus voltage drop across the thyristor. So this voltage will be little different. That we will discuss with the help of the one of the question. So that's why now I'm actually leaving that one, so we can discuss with the help of example. So that's what we discussed about the step down converter. Now we will discuss about the step up converter. In case of step up converter, you can see that like here inductor is there, and then thyristor is connected like this, diode will be like this. So equivalent circuits I have given already here. We can take this one equivalent circuit for T on. Okay, so this is for T on and this is for T off. Okay, so assume thyristor is turned on. If thyristor is turned on means this is acting as a short circuit. If this is acting as a short circuit, then source will supply the energy to the inductor like this. That means in this case, when thyristor is turned on, energy will be transferred to the inductor. Inductor will be getting charged in this case. So this is my plus and minus. That's the inductor voltage VL. So now by looking at this equivalent circuit, tell me what is the inductor instantaneous voltage? It is source voltage. Okay, now we are actually turning on the thyristor and transferring energy to the inductor. Now if you turn off this conducting thyristor using any forced commutation method, now this source and charged inductor both will supply the energy to the load by forcing this diode turn on. Then diode will be in conduction. Now both will supply the energy to the load like this. That means now inductor will be acting as a source. So charged inductor will discharge in the same direction. That means it is charged in this way, same direction it is discharging, but polarity will be reversed now. Okay, so that's what. So now this one is a source voltage. This is like instantaneous voltage source, like it's acting as a source, and both are supplying energy together to the load. So that means here we are, by turning on the switch, we are making this one as an intermediate source, and then both are getting supplied. That means both are actually supplying together to the load. That means instantaneous source plus this permanent source, both are supplying means that's why we will get more energy here. That means that is why we can actually increase the output voltage. But otherwise what will happen if this inductor is not there means you can't supply. Suppose this higher voltage, assume, how will you supply the power from lower voltage to higher voltage? It is impossible. But why are we getting like that means because of the inductor. We are making this inductor as a instantaneous, that means preparing like a kind of source regulator, and after that when you turn off the switch, both are actually supplying together. That's where we can get more voltage here. Okay, so these are actually aiding in nature. VDC plus VL equal to V naught. So from this equation, what is the VL equal to? VL equal to, okay, VDC plus VL equal to V naught. That's why it is nothing but V naught minus VDC. Okay, that's what. Why we are actually taking this means this voltages are required to calculate the average value. It's basically we discussed in the beginning of the class, average voltage across the inductor for the periodic current is always 0. That's what we are taking that. So average current, average voltage here means it will be constant VDC. Here this is also constant, and time period is T on here T off. We can use that one to calculate area under this curve. That's nothing but VDC into T on. Okay, and you can see that this is positive we are assuming, but it is a voltage is reversed. That's why this will be negative. So negative area we need to consider. That is nothing but V naught minus VDC into T of volt divided by T equal to 0. Now we can see that, so we can actually take it like a kind of VDC, T on by T is nothing but T minus V naught into, you can see that V minus V naught, T off by T we already discussed, it is nothing but 1 minus T, and minus of minus plus, okay, that is nothing but it is VDC into 1 minus D equal to 0. Minus D will give you VDC and minus V0 into 1 minus D equal to 0. From this you can get V0 equal to VDC divided by 1 minus D. So this is the V average equation for step-up converter. So that's what. But this is the general step-up converter operation. But we will not use the same one in case of DC motors. We just reverse that. So in this, as I told you, that step-up chopper will be used for the regenerative braking. In that case, what we will do, that motor will be operated as a generator. That means now this will be operating as a source, okay, and this is nothing but will be acting as a load. Operation will be same, nothing will be different. Source and load is actually no difference at all. Only the difference is like here, so source and load is actually interchanged. Because of that, now the equation will be little different. Load is nothing but this one, that's why VDC equal to V0 by 1 minus D. So this is what. Okay, remember this is only for DC motor application. DC motor application. So if the load is DC motor, then in that case we need to use reverse. In the previous one is for generally for resistive and inductive load. If it is not the motor, then we need to interchange both the things. If it is a motor, this is the operation. That means when the switch is actually turned on, then this energy will be stored in the inductor, and when switch is off, then this motor and energy stored in the armature inductance both will supply energy to the load like this. So that's the operation generally. Okay, so we'll see the remaining things in the next video.